Hi and welcome to this video lecture about Heisenberg's uncertainty principle. So, Heisenberg's uncertainty principle states that delta p multiplied by delta x shall always be greater or equal to Planck's constant with bar divided by 2. So p is simply momentum and x is position. And h bar, that's a very small number, it's 6.67 times 10 to the minus 34 divided by 2. So what this equation states is that you can only have enough information about momentum to know the momentum, given that you have no information about the position or vice versa, meaning you can only know either the momentum or the position of a particle. So why this occurs is simply because if you take an electron, for example, an electron is extremely small. So if you were to measure it with a wavelength like this, you will see this is not in proportion or anything, but it is way too small to detect this small little electron. It's way too big. So light has a general wavelength of about 5 times 10 to the minus of 5. And a proton, or I mean in this case an electron, has a wavelength of about, an electron here has a wavelength of 10 to the minus of 18 meters. And a wavelength is, or light has a wavelength of roughly 5 times 10 to the minus 5 meters of a wavelength. So in order to measure it, you need to reduce this wavelength, make it smaller. And by doing so, by sending radiation at this electron, you will start to see a problem, because as we know, if you shorten the wavelength of a particle, you know that the momentum will go up, simply because of this. We know that P, momentum, equals h over lambda. And we came to this equation. I actually explained this in an earlier video, but I can do it again. So to get to this equation, you simply use the term E equals mc squared, which states then that mass is E over c squared. And we know that from classical mechanics that momentum is mass times velocity. But since light has no mass, it won't have a momentum, and we know that that is simply not true. So we know that mass can be written in this form instead, E over c squared. So we know that P equals E over c squared multiplied by c, which is the speed of light, of course, which simply is then just E over c. And Einstein described in the photoelectric effect that energy for a photon is quantized and comes in packets of h bar, of h, Planck's constant. And he said that energy for a photon is simply h multiplied by its frequency. So we can put this term, new energy term, in, and you will find that P equals hf over c, which simply is h over lambda. So we know, since P equals h over lambda, we start to see the problem here. Since h is a constant, we know that by making lambda smaller, we will increase P. By dividing by a smaller number, you will get a greater value. So by making the wavelength small enough in order to see the electron in the first place, it will carry so much momentum and energy, so it will just knock the electron out of place. So you cannot have any kind of accurate measurement to know where the electron is. It is like if you have a pool ball and you hit it with another pool ball with a great velocity, that pool ball will just skyrocket away, and you will have no idea about its momentum, but you can have some idea about its position, for example. And that is the core problem with Heisenberg's uncertainty principle that Heisenberg tried to describe. So this becomes more obvious in the single slit experiment, which basically is You have two walls with a small slit in between, and you send electrons through here. When the electrons get through the wall, they will scatter. And they will scatter with an angle theta. And on the other side of this experiment, we have this detection screen, which feels the electron when it hit it. So you will get a pattern that looks something like this, where you have a lot of electrons in the middle. This is the maximum, and then you have pretty much 0 electrons here in the minimum and here, a little bit fewer electrons here, and so on. So if we magnify this experiment, we make this little bit. We just magnify. We zoom in on the experiment. We see this. So we have the electron that goes through like this. The light or whatever goes through like this. And if we draw another angle, 90 degrees, what do you call it? Perpendicular? I don't know. To this angle, and you know that this angle here is theta. By geometry, you know that this angle here then must be theta as well. So these two angles are theta. So these waves interfere with each other, and they actually cancel out. And because if you have one wave that goes like this, and another wave that is opposite to that wave, they will produce another wave. Nothing. They will cancel out. And why this happens is pretty simple. If we enlarge the view even further, you can just draw actually a triangle like this. And you know that this length is lambda, this is d, this distance here, d. So if you have a wave here, that wave will cancel exactly at half lambda. So if you draw perpendicular at half lambda, this is lambda divided by 2, you will find that this point right here will cancel out with this point right here. So if you have a wave here and here, they will cancel out. A wave here and here, they will cancel out. So waves which where there is a distance between them that is lambda over 2, they will precisely cancel out. So let's do this single slit experiment again. So here's the first wall, the second wall. In between here we have the slit, and we shoot an electron through. So this electron will scatter, as I said before, to a detection screen right here that fills where the electron is. So we know that the distance here is still d, and the angle of scattering is still alpha, theta, I mean. So we know that lambda equals d sine theta. Since lambda is a constant in this case, if you make d any smaller, you will increase theta. So by making the slit smaller, you will increase the scattering. So this angle theta will actually get larger the smaller you make d, due to this equation, right? So we also know that d is a measurement of position in the y direction, if you so will. So this is simply delta x, because up here you will know that the electron passed somewhere between here and here. The uncertainty is here. You know that the electron did go through between this point and this point d. And we know that p is simply the momentum of the electron, P is simply the momentum of the electron here. And we know that that will have uncertainty as well, which is simply the length here, delta p. So we can actually describe delta p now by simple trigonometry, is it right? As delta p equals p sine theta. And we know that p equals h of lambda, which, or sorry, lambda, not x, h of lambda, which we can derive as lambda equals h over p, which is simply d sine theta, as you can see in the picture. And we know now that h is, by deriving this equation further, you know that h, by multiplying in p, is simply then d momentum sine theta. And we know that d equals delta x. Let me just bring that down for you. We know that d equals delta x. We also know that p sine theta equals delta p. So we take these terms, and then you get h bar is simply then delta x delta p, which is not it's not Heisenberg's uncertainty principle, because there are a few inaccuracies in deriving the equation in this sort of way, but it gives you a hint of how Heisenberg's uncertainty principle works. So thank you for watching this video. I hope to see you in a future video. Thanks.